that? Okay, yeah, we've done this for so many other people. Welcome, Willow. We didn't think to record this until now, so you'll have to read that. So if the titrant is active, but the analyte isn't, then you would expect something like that. Or maybe both are active. And then you would expect, let's see, this is current again, be applied. You would expect to see something drop and then go back up. Right? Because remember, your analyte is being depleted, but your titrant is being completely consumed until you get to the end point. Now your analyte is completely consumed and you start adding more titrant and the concentration of the titrant goes up. So its current would go up. We can use it for quantitative analysis. And all of the techniques that we've talked work. So you can do standard curve, the technique that you're probably the most familiar with. So you have limiting current versus concentration, and you get some graph and you can figure out where your unknown is on that. You could use an internal standard because the number of electrons that flow is current. And so we could have maybe a current due to our analyte, and at some other potential, a current due to the standard. So maybe this is our analyte, and that's our standard. They are occurring at different half-wave potentials. But if we know how many electrons flowed here because we know the concentration of this stuff, we can figure out how many electrons must have flowed there, and therefore what's the concentration of that stuff? Because 1 mole of electrons is a mole of electrons. Doesn't matter where it came from. So this axis is going to be consistent.
What does that first word say?
Internal, there,
No, on the graph.
analyte.
Okay.
Remember that we have to get the difference in the E1 halves to be in the ballpark of 0.3 volts. Otherwise, these things overlap. They don't behave independently. That ends up being bad. And everybody's favorite quantitative technique is standard addition. And this one's not nearly as bad to deal with as when we talked about it last time because it doesn't have a log term buried in it. And in fact, it's actually quite straightforward. So we can say the limiting current due to our unknown is simply some constant. You know, it was in the area of the electrode, the diffusion coefficient, what else was in there? Wasn't gamma in there as well? You had a whole bunch of things in that equation, all of which were constants as long as you don't change the electrode. And so it's a constant times the concentration of our unknown. Let's call this equation 1. Add your standard. So you add known volume of, let's call it concentration standard, of a known concentration. Right, that's standard addition. When you do that, we'll get equation 2. That is the limiting current of our unknown plus our standard, which is equal to, I'm going to need more space to write this, just a second. K times the concentration, right? But what's the concentration in solution now? It's got a contribution from the unknown and a contribution from the standard. Remember, the standard is the same as the analyte. If you were trying to determine how much lead is in the water, you measured the lead current in the water, and then you added a known amount of lead 2 plus, and that's the standard. So the concentration, or the concentration now, I'm going to do it in two pieces, would be the concentration of the unknown times the volume of the unknown divided by the volume, let's label this unknown this way, plus the volume of the standard, right? This is going to tell us how much, what the current concentration of due to the unknown was, plus that same K times the concentration of the standard times the volume of the standard divided by the volume of the unknown plus the volume of the standard.
Is that like what you're plugging in for the concentration, or is it the concentration times?
This is what the concentration must be in solution. It must, right? We had, so let's do the lead example. We had some lead 2 plus in the water. We don't know how much, but we know there was some there. And we intentionally added some lead 2 plus, and we know how much we added. But this is how you would figure out. There would be a term related to concentration of our unknown. The unknown was diluted. It was diluted by that factor. And we have a concentration of lead due to the standard. This is the concentration of lead due to the standard currently in solution. It's the amount that we added times its concentration diluted by the total.
Oh, so C standard
So
is a
let's use this is concentration of the standard, or due to, and this is due to C unknown, right?
So it's like C unknown times volume divided by.
Right, because what we had lead there, but we added more water to it when we added the standard, and so we've diluted it. Okay, this is now a math problem. Two equations, two unknowns, because we don't know K and we don't know C unknown. Solve it. And you could solve it by a myriad of ways. I went through it. I'll go through it. I'm going to divide equation 2 divided by equation 1. And I'll just do this for you real quick and get to the end. So we have the limiting current due to unknown and standard divided by the limiting current of just the unknown is equal to K C unknown times volume unknown over volume unknown plus volume of the standard plus K, oops, that's not really there, C standard, B standard over V plus V standard divided by K C unknown.
Doesn't that just cancel it out or no?
Pardon?
Doesn't that just cancel KC unknown? If you're, oh, that's all in parentheses.
This is all in the top. Yeah. So we're going to multiply by C unknown, and I'm going to define this term as R. So the current, so we don't have to keep writing this current divided by that current. Let's just call that current R, or that ratio of currents R. So that's going to give me on this side, R times C unknown is equal to, oh, when we do that, right, we're going to get C unknown over here K is a constant now, so K is going to disappear. Now we can get rid of the K. And that leaves us with C unknown times V unknown over V unknown plus V standard plus C standard times V standard over V unknown plus V standard. Multiply by the term that's on the bottom. That gives us R C unknown times V unknown plus V standard is equal to C unknown plus times V unknown plus C standard times V standard. Collect terms. We want to collect all the terms that have C unknown in it. And that's going to give us C unknown times R V unknown plus V standard minus V unknown is equal to C standard times V standard. Divide by this term and you're there, right? Okay. Probably would be easier to do it if we'd actually had numbers in there, but it can be done. And that one's not so bad. Doesn't have log terms in it. And you need to get comfortable with standard addition. It's a common technique. You could have used it for the HPLC and eliminated a bunch of standards. But then you wouldn't have been able to share standards, right? Because it would be your unknown plus a standard. The advantages of standard addition is you can do it with a lot less samples. Whereas you need a good calibration curve to do the technique you are most comfortable with. You can do it with a single standard there. Now I never did, I always did multiple standards, but it has the power to do it with one standard addition. Okay, so that wraps up hydrodynamic voltammetry.
Can you wait to erase that last part?
Yes.
And on the very end of that top equation, is that V standard?
Tell me when you've got it, because I want to put the screens down.
Okay.
So that means we can move to the second technique, which is polarography. Recall that polarography has no stirring and uses a dropping mercury electrode. Question or just stretching, Caroline?
Just a stretch.
So this is a polarigram. This curve. Remember what's happening. We have a dropping mercury electrode. So that means you start off with no mercury, and the drop grows, and then falls off. You start with no mercury, the drop grows, falls. So the electrode surface is changing. And that's what you see as what looks